So, hello everyone. Welcome to the live section of this course, which is Fundamentals of Classical Electrodynamics. So, I'm Gitanjali. I'm a research scholar from IIT Delhi and I'm the TA for this course. So, in this live session, we will go through the weekly content, and now we are in week 10. We'll briefly go through the concept of week 10. And after that, after reviewing the concept, we'll solve few problems that is related to the concept of week 10. So before starting the session, let me ask whether my voice or my screen, is it visible to everyone? Is it okay from your side? My voice and the screen, are you able to see that and are you able to hear my voice? Okay. Okay then. So let's start our session. So in week 10, we basically see what is a vector potential. So similar to electrostatics where we have scalar potential for a conservative field. So if you recall, we have for the electrostatic case, call of E is zero. And for that case, we have concluded that we can represent electric field as a some gradient of some scalar function. Similarly, in magnetostatics, we have the uh, divergence of J should be zero. And you can recall the divergence of B is always zero for this according to the Maxwell's equation. So using this, you can easily, and we know that divergence of curl is always zero. So it's a mathematical definition. So that is why we can always write magnetic field in terms of some curl of some vector potential A. Okay. So vector potential, similar to the scalar potential, it's if you add any gradient of some scalar function to this vector potential, then you can get a new vector potential. But the thing that don't change is the magnetic field. So even after you add a some gradient of some scalar function to this initial vector potential, so the magnetic field won't change. So it remains same. Uh, which book? Okay, the question. Practice. So, for the exam point of view, I think it's sufficient if you go through the um, whatever questions that has been asked in the assignment. Also, the questions that I am solving in the tutorial session. So, no need to solve many more problems because I am trying to cover the important question from all the books. Like I am taking question from Griffith and outside Griffith. So I think it will be fine if you go through the assignment problem as well as the tutorial question. So if you're getting extra time, then you can look at books. You can look at the previous year question of any competitive exam. So you can look at that like say Net, Gate or JEST. But I also try to cover that question in the tutorial session. So in case I have not covered any question, then you can look at that competitive exam. Uh, there is no particular book that uh, um, whatever book is there, they have covered the advanced problem, so it's not required for you. So try to cover. So I would suggest try to cover the assignment problem as well as the tutorial question. Okay, and the questions from Griffith, I think it's sufficient for you to tackle the exam. Okay, so So when you add any gradient of some scalar function to this vector potential, then the thing that don't change is the magnetic field. So this may conclude that this may mislead you to that there is no physical significance of this vector potential. It's just a mathematical definition to calculate the magnetic field. But in reality, it's not. It's vector potential does have some physical significance, and if you see, you will see in the latter course that there is an famous quantum mechanical effect, which is Aharonov-Bohm effect. So I think some of you have already know what is this effect. So this effect emphasizes the what is the importance of a potential in a charged particle. So even in brief, it this effect shows how in a region where you don't have any magnetic field or any electric field, even in that case, the charged particle will experience and will the physical behavior of this charge particle will change because of this vector potential. So this is what is the famous Aharonov-Bohm effect. So this indicates that the vector potential does have some physical significance. So it's not just a mathematical formulation to calculate the magnetic field. Okay. So, besides that, we have seen in magnetostatics, you can write divergence of B is mu naught J. So that means the source of magnetic field for the magnetostatics, it's a current density or a current carrying wire. So for magnetostatic, you have this relation. And if you put curl of A to this equation, you will get a equation of the form divergence of AR minus del square A is mu naught J. And if you put a specific condition, that is the Coulomb-Gauss condition, where the divergence of A is vanishing, in that case, we are left with the Poisson's equation. So this is one of the special case. And after that, we have also seen a relation to find out how the vector potential is related to the magnetic flux. So if you take the line integral of the vector potential around some arbitrary curvature, so this is equivalent to the magnetic flux associated with that surface. And you can also write it if you use the Stokes theorem. You can also write it as this is BDS or this is curl of ADS. So always try to remember this relation so that it will be helpful for you to solve the problems, numerical problems. Okay. So after that, we have seen how the magnetic potential behave when we are considering in a large distance. So for that case, we have expanded 1 by r in terms of some series, Taylor series, and we have seen the multiple expansion of the vector potential. And for the magnetic dipole, if you recall the magnetic potential, you can write it as mu naught by 4 pi m cross r divided by r cube. This is for the magnetic dipole. After that, what we have seen, the last part is it is basically covering what will happen when you put a magnetic material to any magnetic field. So in that case, what will happen? Besides the free current density, if the material is carrying some free current density, will have a bound current density. So if you recall the electric field case, we have dielectric. If you put the dielectric, there will be separation of charges. So because of that, we'll see volume bound charge density and surface bound charge density. Similar to that, here we have bound volume current density as well as the surface bound current density. And in electrostatics, we have the divergence of JB, sorry, rho B is nothing but minus of divergence of P, and the sigma B is P dot Nk. Here we have the curl operator. So this is curl of M, and this is M cross Nk. M is the magnetization, which is the response of this material in a external magnetic field. So you can write the total current density as total J free current density as well as the bound current density. And if you put this J in the B, the curl of B mu not J, so you can rewrite it as curl of H is J free. So these you have already seen in the lectures. And one condition that we have seen is for linear material, you can write magnetization is directly proportional to the applied field. Applied field is H. So you can write M is chi M H. So in that case, you can write B is the expression for B, it will simplify to mu H. Mu is nothing but mu naught 1 plus chi M. So B is the total response in the presence of a magnetic field. So whenever you put a material, magnetization will occur inside this material due to non-zero value of chi m. So this is M. Then because of this magnetization, we'll see some induced magnetic field. And when you sorry, so when you apply an applied field, so there will be a response to this applied field, which is B. And when you add these H2Ms, the total response will be B. So this is all about the brief introduction to what we have seen in week 10. So now we'll solve few problems that is related to this week. So let us start our first problem. So there is a long cylindrical rod of radius r, which is a magnetization M. It is given by M is given M0 R Kk, where R is the distance from the axis of the cylinder. So you need to find what is the total current enclosed in the cylinder of length L. So total current means you need to look for whether there is any free current is there or not, and you need to calculate what is the bound current. So magnetization is given and there is no information about the free current. That means you can take J free is 0. M is already given, so you can easily calculate what is the volume current density due to the magnetization. This is given by curl of M. And in cylindrical coordinate, you can write it as 1 by R, RK, R phi K, JK, dou by dou R, dou by dou phi, dou by dou Z. And M has only Z component, so this is 0, 0, M0 R. So if you simplify it, it will be 1 by R, R dou by dou R of M0 R phi K. And this is minus M0 phi K. For the surface bound current density, this is M cross Nk at the surface. So M is given, it is M0 R. So at the surface, it will be M0 capital R. What is the radius given? Okay, capital R. And this is Kk cross Rk. So this will give M0 R phi K. So to find out the total current, you need to first find out what is the volume current density. Take the integration. So this is M0 is in the phi direction dot, and the area element in the phi direction will be dr dz, right? Dr dz phi k. So this will give minus M0 R and Z is L. For surface, it is KdL, integration of KdL. So M0R is a constant, and when you take the integration of dl, it will give M0R L phi k. So that means the total current, it should be 0. This is of this you can easily guess if you go through the question. So for all types of magnetic metal, whenever the bound current density, volume, and the surface, they add up to 0. So that means this will be 0. Okay. So the answer for this is, I think, option A. Okay. So let us move to our next problem. So there is a magnetic field corresponding to a vector potential A. So it's given A is half F cross R plus 10 by R cube R. F is a constant vector. So you need to find out what is the magnetic field corresponding to this vector potential. So you just need to calculate what will be the curl of A. So if you see curl of A, you can write it as half curl of F cross R plus 10 curl of this, you can write it as R by R cube. So you need to find out what will be this expression and what will be this expression. It's given that, so first we need, let us see what will be this expression, then we'll take the curl and the total contribution of this first part. So for that, what it's given f is a constant vector. So that means in the Cartesian coordinate, you can write it as, let's say it is f0, some constant f0 ik plus jk plus kk. The position vector, you can write it as xik plus yjk plus zk. So that means f cross r will be, this is f0 ik plus jk plus kk cross xik plus yjk plus zk. Take the cross product. I think this will come f0. I will only take the cross with j and k. So that means this will give y kk minus I cross k will give minus j z jk plus फिर j, this will cross to I and k. So this will give x ij will give minus kk plus z, j and k will give ik. Plus the last k will take the cross product with I and j. So this will be x, ki will give j, and kj will give minus y, minus jk. So final expression will be f0 z minus y ik plus x minus z jk plus y minus x kk. So this is F cross R. So further, if you take the cross product, it's quite easy. So this will give F0. Let us take this determinant form ik jk kk dou x dou y dou z, and this is z minus y, x minus z, and y minus x. So if you calculate it, it will come as 2ik plus 2jk plus 2kk. That means it is 2 times of the constant vector f. So this, and if you take the half of it, because it's half of this value, so this will give, first contribution will give f. Now let us see the second part. Curl of r by r cube, or you can write it as curl of r cube by r square. Anyone can tell me what will be this value? You can easily guess. This is nothing but ik plus jk plus pk by x square plus y square plus z square. So if you take the curl, it will give a value of 0. So that means the contribution will only come from f. So that is why the magnetic field corresponding to this vector potential, which is given by this, it will be the first option A. Okay, so is it clear?4 pi delta QR. So that is for the case when you take the divergence. Divergence of R k by R square, it is 4 pi del QR. Okay, not the cross product. For cross product, it's 0. You can easily guess because for all the terms, it is 1 by R square. So when you put it here, this will give a 0 value. Okay. So let us move to our next part. For this case, there is an infinite solenoid with its axis of symmetry along the z direction carries a steady current I. The vector potential A at a distance R from the axis is. So you need to find out how the vector potential for this long solenoid is behaving as a function of R. So there are four options is given. One is it is constant inside, or where it says R outside, or for B option it is R, it is directly proportional to R inside and is constant outside. For C option it is varying is 1 by R inside, and for outside it is directly proportional to R. And for D it is directly proportional to R and inversely proportional to 1 by R. So for this, I think you can easily guess what will be the form that you need to take. Yes, I think it's option D. And if you recall, so let me quickly go through the solution. So ADL it is curl of ADS, or BDS. And for solenoid, we know that inside only the magnetic field is non-zero. So mu naught Ni, B is mu naught Ni for R less than R, and it is 0 outside. So you know the magnetic field, and what is the direction of this vector potential? Anyone can tell? What is the direction of this vector potential? So direction of the vector potential, if you look at the definition, it is, if you recall in the lecture we have seen, it is mu naught by 4 pi I dl by, I think, r square. So this means it is in the direction of the current. Yes, you can also take it as so it's perpendicular to B, because B is called a phase. But when you consider so if you want a want to take a Gaussian loop, Amperian loop, sorry. So for that you need to see how what is the direction of this vector potential. So for that, this is helpful. The vector potential is in the direction of current. So that means you can take a Amperian loop like this. Okay, so if for using this, we have seen how the answers will be. So when r is less than r, it is a 2 pi r b dA. B is mu naught ni z cap, and this is pi r square z cap. So A, it will be mu naught ni by 2 r phi cap. So it is directly proportional to R inside. And for outside, we have ADL is BDA, and BDA will be mu naught Ni pi R square. So from this you can get this is mu naught and I R square by 2 1 by R pi. So this is how we have calculated what is the behavior of this vector potential inside the solenoid as well as outside the solenoid. Okay. Okay. So let us see question number 4. For question number 4, we have a vector potential which is given is y z I cap plus zx j cap plus xy k cap. And C is a circle of unit radius in a plane defined by z equal to 1, and the radius is 1 with its center on the z-axis. So for this, you need to calculate what is the value of ADL. ADL around this circle. So calculate it and let me know the answer. Okay. So first try to calculate it. Let me see whether you are able to get the answer or not. After that, I will show you the solutions. Try to think which which of this formulation that formula that you can take to calculate the value. How you can calculate approach this question? So for this, one thing you can do is either express x and y in terms of r and take the integration of r from 0 to 1. It's given it's a unit radius. Other thing that you can do is, if you recall the curl ADL, it is, yes, we have to take the line integral across this circle. So if you recall, it's related to the curl of A also, curl of A ds, right? So let us first calculate whether call of A. So if here you can see there is an option of 0. So let us see call of A is getting whether we are getting a non-zero value or not. So if we are getting a zero value, that means directly the answer is 0. There is no need to calculate the total integration. So if it is not there, not 0, then we have to express dx in terms of dr, and we have to take the integration of r from 0 to pi and phi from 0 to 2 pi. So let us see call of A first. And it is quite straightforward because it's a Cartesian coordinate. That means you can easily recall what is the what will be the call for the vector potential. So it is, this is yz, zx, and xy. So this will give x. So dy by this will give x. This will give also x I cap minus j cap. Y part, this will give y, and this one will give also y plus k cap dou by dou x of zx. This will give z. Dou by dou yz. This will also give z. So that means the curl is, we are getting a zero curl. So there is no need to calculate the integration now because it's already 0. That means the line integral is 0. Okay. Let us see question number 5. For question number 5, there is a magnetic vector potential is given. It is given by minus rho square by 4 z cube wave per meter. Calculate the magnetic flux crossing this surface. It's given phi is pi by 2 and rho, the range is from 0 to 2 and z is from 0 to 5. Calculate it and let me know the answer. There is a question. Can we say that line integral in a closed loop is always 0? Actually, it depends on A, because if A is varying, then I think in that case, so Only in that case when A is behaving like some constant, in that case, this will eventually come out as zero. But I think if it is some non-zero function of, if you are getting some variable here, uh, I think for that, for some of the cases, it will come out as non-zero. That is what I can think of. Or magnetostatics, like in the electrostatics, EDL is always zero because the call is always vanishing. But here, only here it is not the case. It's like call is not always vanishing. Mm. So I think you can't take ADL is, you can't directly put ADL is directly zero if it is a magnetostatic case. Let me see whether it is always valid or not, and I will let you know the answer. Okay. Okay. Question number 5. What are you getting? Vector potential is given and the ranges are given for the surface. You need to calculate the magnetic flux. That is BDS. Okay. So because A is already given, that means you can calculate what will be B. B is nothing but curl of A. And this is a cylinder, sorry, this is a cylindrical coordinate. So take the call expression for this cylindrical coordinate, which is I think 1 by R cave, R phi cave, Z cave, dou R, dou phi, dou Z, AR, RA phi, and AZ. So if you put the expression, only AZ is given, these two are zero. So that means here you will get curl of A, it is minus of dou Az by dou rho phi cap. So that means this will give rho by 2 phi cap. So we know B now. Flux is nothing but BDS, right? DS for this case, in the phi direction, it is d rho dz, right? So that means magnetic flux, it is BDS. B is rho by 2 d rho from 0 to, sorry, from 1 to 2, and dz is from 0 to 5. So from here, this will be rho square by 2, 1 to 2, and this is 5. And I think there is a half also here. Okay, half is already there. So this will give 3.75 Weber. Check the answer. I think you will get option C, if I'm not wrong. Option C, I think it's option C. Yes, I've already included half. Oh, this will come out as I think 15 by 4. So from that it will come 3.75, right? Yes. Okay, I think you are indicating to row D row. Okay. So there is one half there. I missed this half. So this will be rho square by 4, and rho square by 4 will be, so 4 square minus 1, 3 by 4, 3 by 4 into 5. So 15 by 4. 15 by 4, it's a final answer. Option C. Any doubt in the question? Steps are clear, right? Or you need me to explain again, or can I proceed? Okay, so if it is clear, then let us move to our next problem. For this, we have a toroid which have an iron core with a square cross section. It is wound tightly by n closely spaced turns of wire carrying current I. Find the magnitude of magnetization inside the toroid. There is a toroid which is iron core, and the number of turns is n is given, and they are carrying current I. Find the magnitude of magnetization. So for magnetization, we need the information about B and H, right? Because if you recall, B by mu naught, B is mu naught H plus N, right? So you need the information about B and H. It is quite easy because you can use the Ampere's law, H dl. This will be total free current, which is total number of turns N is given and current is I. So this means H is Ni by 2 pi r. And for a linear material, you can write M as chi mh, right? So, or you can let us see M is d by mu naught minus h. And for linear material, we have this is mu h minus mu naught minus h, or mu minus mu naught, mu minus mu naught by mu naught h. H we already know, this is Ni by 2 pi. Uh, so according to that, answer will be option D. Okay, so let us move to our next problem. So there is a, the magnitude of magnetic dipole moment associated with a square shaped loop carrying a steady current I is M. So there is a square loop which is carrying steady current I, and it is given its magnetic dipole moment is M. Now we are transforming this square loop to a circular shape, which has same current I passing through it. So what will be the magnetic dipole moment here? Calculate it. It's quite easy. Recall the formula for the magnetic dipole moment. So there are two formula that has been given in the class. Recall it and let me know the answer. Current is same for both cases. First case we have magnetic dipole moment M. In the second case we have magnetic dipole moment M prime. Option A. Okay. Yes, it's correct. It will be option A. So if you recall, the magnetic dipole moment is nothing but the current into area. And for this square loop, let's say it is a side of length A. So M should be I A square. For this, it will be I into pi r square, right? R is the radius of this circle. And we don't know the relation of R with A, but we know that the same square loop is transforming to this circular loop. So that means the total length during this transformation, it should be same. So total length here is 4A and the length, which is the perimeter here, circumference here, this will be 2 pi r. So that means r is 2a by pi. So m prime is I pi r square, which is 2a by pi square. So this will be 4 by pi I a square. And I square is nothing but the dipole moment where we have a square loop. So this is 4m by pi. So answer A. Okay. Let us move to our next problem. Let me solve it. This will take some time to solve it because there are a lot of parameter to calculate it. So there is a cylindrical conductor of radius A and permittivity mu. There is a z-directed uniformly distributed current I. So let us draw it first. There is a radius is A, permeability is mu, Z directed uniformly distributed current. So current is flowing in Z direction and it is uniformly distributed. First part, you need to calculate what will be the magnetization M within the conductor. Second part, for this magnetization, determine what are the values of the surface and the volume current density. So for magnetization, we need the information about H, right? So first find out H first, and H is related to the free current. So we need to use this Ampere's law. HDL is I free. So we can take a Gaussian loop, and this is, let's say this is small r, or Let us take this as S. So for S less than or equal to A radius, the total free current enclosed is, it is uniformly distributed. That means this will be pi square by pi A square, which will be I A square by A square. We know the current, then H dl is I A square by A square, and this is H 2 pi S is by A square. So H is I by 2 pi A square S phi cap. This is for inside. For outside, the total free current will be A, right? Sorry, I. So that means H is directly I by 2 pi S phi cap. So we have H, it is Is by 2 pi A square phi cap. And this is for the inside, and for outside it is I by 2 pi S phi cap for S greater than A. Now it's quite easy to find the magnetization. So magnetization within the conductor, this we need to find out. M is Im H. H is we all know. So this will be Im Is 2 pi A square phi cap. Or you can rewrite it as Im is mu by mu naught minus 1 Is by 2 pi S for inside the cylinder. For outside, you put this is Im I by 2 pi S phi cap or mu by mu naught minus 1 I by 2 pi S phi cap. But the thing is, it is outside. The reason we are considering is the outside region, right? So for this region, mu is mu naught. So that means the magnetization outside, it's trivial, it should be zero. So we have calculated the magnetization. Then we need to calculate what is the volume and surface bound current density, which is quite easy because we know the magnetization now. So volume current density, it is M is, sorry, J, J bound due to magnetization. It is curl of M, right? So one thing you can do is, you know, the expression of this magnetization, put it in the curl equation using the cylindrical coordinate and find out what will be the jm that you can get. Other thing is you can get it directly by writing the expression of m. So no need to find out the curl. So this is curl of chi mh, and if you recall, Im, this is curl of H. Curl of H is nothing but the free current, right? Sorry, free current density. And inside the free current density is this will be, because it is uniformly distributed, you can write it as I by pi a square. So you will get the same answer if you take this expression and put it in the curl expression, and the answer will be same. But for this, the approach, it will take few minutes to find out the answer. Okay. Okay. So this is about the volume bound current density. For surface, so JB we have found this is chi m I by pi a square. For KB, it is the surface current density. It is m cross n cap. At the surface, radius is a. So this is a chi m I by 2 pi a phi cross cap, which is chi m I 2 pi a z cap. This will be the surface bound current density. So we know JP, we know KB, we know magnetization. If you want to further calculate what is the magnetic field, then you can use B is mu H, right? H you already know. So this you can directly use. This will be mu naught. Mu is mu naught 1 plus chi m is by 2 pi a square for s less than a. And it is mu naught I by 2 pi a for s greater than a. Is it clear? So let us move to next problem. Uh, there is which one of the following expression for a vector potential A doesn't represent a uniform magnetic field of a of magnitude B0 along the z direction. So calculate it. Let me know the answer. Option B. No, I think it's option C. Option C is the answer. So it's given which of this following it's not. Don't give a magnetic field, uniform magnetic field along the k direction. So that means which of these following is not satisfying this? Okay, then it's fine then. So I think we followed this step only. You just need to put the value of A here in the call equation and see which of this it's not giving B as B0 gate. Steps are quite easy. You just need to use the call operator and the values that is given. Okay, it's quite easy, so let me skip it. For next question, so there is a constant magnetic field of zero point 0.6 Tesla along the z direction. Find the value of the path integral ADL in the units of Tesla meter square on a square loop of side 1 by root 2 meters. Then, okay, so magnetic field is given, it is zero point 0.6 Tesla. Square loop of side length is present in this magnetic field 1 by root 2. Length is 1 by root 2. And the normal to the loop makes an angle 60 degree to the z axis. Okay, figure is not given. Let me draw it. So there is a magnetic field in the z direction and there is a square loop. And the normal to this square loop, it makes an angle 60 degree with the magnetic field and the length it is given 1 by root 2 and B is zero point 0.6 Tesla in the z direction. So what will be ADL? 0.15. Yes, you're correct. So ADL, I think you have used the relation. ADL is BDS. Is the magnet, it's related to the magnetic flux. And for this B is all, you can write B as B0 KK and ds is some dx dy or you can write dA some normal vector direction nk and b0 is a constant dA and the dot product of k and n will give cos 60, right? So this is b0 cos 60. Integration of dA will give the area of this square, which is 1 by root 2 square. So it is half. So b0 by 2 cos 60 is also half. This is 0 0.6 by 4. 0.15. Yes, 1.5. Okay, good. Let us see our next question. This question is also easy. Calculate it and let me know the answer. So there is a vector potential A, which is alpha x k plus 2y y k minus 3z z k. And it's given it's satisfying the Coulomb Gauss. And for this to happen, what will be the value of alpha? Okay, yes, the answer is correct. Coulomb girls, it is divergence of A should be zero. So dou x by x, dou y a y plus dou z a z should be zero. And it's dou x by x is alpha plus this is 2 minus 3. That means it is 1. Okay, so let us see our next problem. Let us solve it. So there is, so you need to find out what will be the vector potential due to a two parallel straight currents I flowing in the plus z and minus z direction. So there are two wires carrying current in opposite direction. You need to find out the vector potential for this wire. Let us sort it. Let us say we have one wire. Let us calculate for one wire and then we can add for the second. Let us say there is a current carrying wire which is perpendicular to the xy plane and it is carrying current in the positive z direction, and we need to go, and we are finding out the potential at the point P, which is some arbitrary coordinates xyz, and in the plane this distance, in the xy plane this distance is r. So if you look at the xz plane, so for that, so to calculate the vector potential, if you recall, AR is mu naught I by 4 pi dl by r. So dl is dz here. So there is a length element dz, which is at a distance z. And this distance, it's in the xy plane r. This is square root. This is the p point. This is r square plus z square. Direction of A is always along the z direction because current is along the z direction. So AR is now, it is mu naught I by 4 pi dz, r is square root r square plus z square from infinity to infinity. So this is the even function. That means you can write this as 2 times mu naught I by 4 pi 0 to infinity dz square root r square plus z square. And the integration limit, integration value is logarithm function. So this is 2 mu naught I by 4 pi log z plus square root r square plus z square from 0 to infinity. So after putting the limit, you will get this will come around 0 and infinity. So this is minus 2 mu naught I by 4 pi log r. And there is some divergence constant when you put the infinity term. So this doesn't change the value of b. So we can neglect it or we can keep it as it is. There is some constant here. So this is for the one straight wire. So AR is minus mu naught I by 4 pi Oh. Now we have two wires, two parallel wires, and they are carrying current in the opposite direction. So this is in the positive direction, this is in the negative direction. Current is same, minus I, this is I. Let us say this distance is minus A, this is A. And we need the distance from the point P. XY plane, the coordinates are R2 and this is R1. This is X, Y, Z. So we can use it. So AR will be superposition of the vector potential due to first wire and vector potential due to the second wire. For the first wire, this will be minus mu naught I by 4 pi log R1, right? And for the second wire, it is, so current is in the negative direction, so minus will become plus mu naught I by 4 pi log R2. So this will give mu naught I by 4 pi log R2 by R1. And R2 R1, you can see this figure. R1 square is x minus a square plus y square. R2 square is x plus a square plus y square. So this will be the vector potential due to two parallel wire which are carrying current in the opposite direction. For the same direction, you can easily find out because here only the sign will change. This will be minus. So this will be like mu naught I by 4 pi log R2 R1. So I hope this solution is clear to you. If not, let me know. And now let us move to our next problem. So there is a infinitely long cylindrical cell of radius A and a negligible wall thickness carrying current I along its axis. Find the vector potential produced by it. So if you recall, B is 0 or R less than A, and it is mu naught I by 2 pi R pi cap for R greater than A. And for vector potential, this is related to curl of A. Direction of A, it will be either be parallel to the current or it will be anti-parallel to the current. So it will be in the Z direction because it's given I is along its length. So A will be along its length. Let's say the length is along the Z direction. Z direction. So if you see B, it has a component along the phi cap direction. So from here, B is in the phi cap direction. And we are saying A should be in the Z cap direction. So that means you can, in the curl equation, you can neglect few of the terms so that you can get the value of the vector potential. So in the curl equation, if you look at the cylindrical coordinate, this in because in the left hand side you have a component along phi cap direction. That means this part should have the component along the. You should take the component of curl which is in the phi cap direction, and that is dou az by dou z minus dou az by dou r phi cap. And it's also we are saying A should be in the z direction. So that means there will be no variation of this vector potential along the z direction. So this term it vanishes. So we can neglect this term. So we are left with only one term, which is B is minus of dou Az by dou R phi cap. So B phi is minus dou Z by dou R. Let us put the value of B. B is mu naught I by 2 pi R. Mu naught I by 2 pi R. This is minus of dAz by dr. You can replace the partial with the total because A only has Z component. Now we can solve it. dAz is minus of mu naught I by 2 pi R dr. So Az will be integration of dr by r, it will give ln r plus some constant that we can get it from the boundary condition. So this is for the inside one. Sorry, for the outside one, we have the potential like this for r greater than. For r less than a, v phi is 0. It's given it's 0. So that means dou is it by dou r, it should be 0. So Az is some constant which is satisfying this differential equation. To find out the value of constant, one thing you can do, you can put one of this constant is 0, and you can write the value of other constant in terms of by equating the boundary condition. So for this case, you can either put C1 is 0 or C2 is 0, it doesn't matter. So let us put C2 is 0. So if C2 is 0, that means AZ inside is 0. And at the boundary, that is at R equal to A. So inside should be equal to the outside. This is for the inside. So this is 0, and outside it should be mu naught I by 2 pi ln A plus C1. So that means C1 is mu naught I by 2 pi ln A. Okay. Put the value of C1 here. So this will be mu naught by 2 pi ln A by R for the inside, and for the outside AZ is, sorry, for the inside AZ is 0, and for the outside you will get mu naught I by 2 pi ln R by. So is this problem clear? Do you have any doubt in any of these steps? This R greater than A. And for outside, for inside it is 0. Question is, this is the question. Is it visible or it's not visible? Okay. So should I proceed or you need some time to go through the solution? Is it okay now? Okay. Okay, let us move to our next problem. There is a long cylinder of radius r. It carries a magnetization M. Magnetization M is given. So there is a long cylinder. Magnetization is given as it is K r square by K. K is a constant and R here is it's the distance from the axis of the cylinder. So this is R. Phi k is the circumferential unit vector. Find the magnetic field induction B due to M for points inside and outside the cylinder. So we need to calculate what will be B, right? So M is given. So let us first calculate the bound current densities. From that you can calculate H and H, or you can directly calculate the total current. And the total current we can calculate what is the B. So let us see first the volume current density. JB is curl of M. So it is cylindrical coordinate. So I'm directly writing the final expression. Cross verify it. If you are getting some other value, let me know. M phi is KR square. So this will be KRQ. So this will give 3KR square. So 3KR ZK. JB is KKR ZK. For KB, it's quite straightforward. This is called cross and at the surface. Radius of cylinder is capital R, so this will be K R square pi cross R cap, which will give minus Z cap. So we know what is the volume bound current density. Let us calculate the enclosed current. So there is, it's not given there is a free current, right? So the cylinder is not carrying any current, only it is placed inside the magnetic field. So that means only the contribution will come from the bound current densities, both the volume and the surface. So if you look at inside, only the volume will contribute, and for outside point, both the volume and the surface will contribute. So if you look at the inside, so this will be JB, DA perpendicular. So JB it is 3KR, and the area vector in Z direction, it will be RDR d phi, right? RDR d phi. So DA perpendicular I am taking by looking at the at which direction the volume current density is pointing. So it is in the Z direction. So that means we have to take the area element in the Z direction. So this is 3KR RDR d phi. So this will give 3K R square dr and d phi is 0 to 2 pi, 0 to for inside 0 to small r. So this will give 6 pi k r cube by 3, which is 2 pi k r cube. We know the total current for a inside point, so we can use the Ampere's law. BdL is mu naught I enclosed. I enclosed is 2 pi k r cube. So B is mu naught 2 pi k r cube by 2 pi r. This will cancel. So B is mu naught k r square phi k. And kr square is nothing but this whole term is magnetization. So B is mu naught m for the inside one. For the outside, you can easily guess the total current should be zero. Or you can get it by taking the integration. So I enclosed is JBDA perpendicular and KB DL. JB is CKR, or we can directly to take the value of the integration. This is 2 pi KRQ. This we have got for the outside. The JB will run from 0 to capital R. So this will give 2 pi K R Q. And KB is KR square minus KR square minus KR square DL perpendicular. So what is the DL perpendicular? You can take it here. So for that you need to look for the direction of this KB. So it is in the direction of Z. So you need to take the area, sorry, not the area element, length element in the Z direction. The Z direction, the length element is d phi. This is 2 pi KRQ minus D5 will give 2 pi. So 2 pi KRQ. So that means total current is 0. So B should be 0. So B is 0 for R greater than R. And this is mu naught M for R less than R. Okay, so let us move to our next problem. In question number 15, it's quite straightforward. So there is a constant uniform magnetic field. B is B0 kk, which is all over the space. Which one of the following is the correct choice for the vector potential in Coulomb guys? Calculate it and let me know the answer. So given B is present, it is B0 kk. And which one of these following vector potential is representing the Coulomb guys? Option D. Let me see. I think it's option C, not D. Divergence of A should vanish because it is in the this is dy, right? So if you take the divergence, it should be it will come out as 0. This part it will give a non-zero value because the x part will give a non-zero value. For this, the y part will give a non-zero value. And for this also, it is b0 by 2x. So when you take the divergence, it will come minus up. Okay. And for y also, it will give half, right? So for this case also, it will give a zero value. Now the question is, in these two options, which one of these following will give a magnetic field of B0 kk? Whether both the options are giving the B0 kk or not. So let us see. So if you take A is minus 1, B0, all of Let us take out B0 by 2. So this will give minus 6 and this will give y. You can see it here. This will give a value. Sorry, let open. So this will give a value of 0. Even though it is satisfying the Coulomb Gauss, okay, for this you need to be careful also because here you can. So here it is two of this option is giving the Coulomb Gauss, but one of is satisfying the magnetic field is B0 K. Uh, what is happening? Please wait for 1 minute. I think there is a problem in my iPad. Let me rejoin it. Let me rejoin the iPad and giving some error. Let me reconnect. Please wait for, I think, 3 minutes. Mm, okay. Let's- Okay, so let us see our next problem. It's also based on the, I think it's based on Coulomb Gauss only. No, it's a different one. So for this, there is a vector potential inside a long solenoid with n number of turns, unit length, carrying current Y, uh, which is in the cylindrical coordinates. So A is given, A is phi Z, it is mu naught Ni by 2 S I cap. A is given. Now we are adding a term. If the term, which is this, where alpha is not 0, beta is not 0, is added to the previous potential, the magnetic field remains same. Then how the alpha is related to beta? If the magnetic field, even after adding this factor, the magnetic field is not changing, then what is the relation between alpha and beta? So for this, let us first calculate B. We can calculate B for individual cases, then we can equate it so that we can find out the relation between alpha and beta. So B for the first case, it is call of A. and this is 1 by S, K is 5 K, Z K, dou by dou S, dou by dou phi, dou by dou Z, A, AS, SA phi, and this is AZ. AS is given, this is 0. SA phi will give, this is the A phi. This will mu naught Ni square by 2. AZ is also 0. So this will be 1 by S. And the only non-zero term will be this one. Dou by dou S of mu naught Ni S square by 2. So this will give mu naught Ni 2S by 2 Zk. So this will give mu naught Ni Z. So like the field due to a solenoid. So B, this is the previous case. Now we are changing the potential A to A prime. This is A plus, we are adding mu naught NIS by 2 alpha cos phi cap plus beta sin phi SK. This is this is also given mu naught Ni by S by 2 phi cap. So A prime is mu naught Ni S by 2 1 plus alpha cos phi cap plus mu naught Ni S by 2 beta sin phi. So what will be the magnetic field now? B prime is call of A prime, which is 1 by S by S cap S phi cap Z cap dou S dou phi dou Z. S for S, you can put this one, and for phi, this is the, let us say this is AS, this is A phi. AS A phi 0. When you take the derivative, this will come 1 by S mu naught NIS alpha cos phi plus 1 minus mu naught NIS by 2 beta cos phi. So finally we have mu naught Ni alpha cos phi plus 1 minus beta cos phi by 2. These magnetic fields are equal. Previously we got mu naught Ni. Now we are getting this value. So for this to be equal, we should have alpha cos phi plus 1 minus beta cos phi by 2, which should be 1. This will cancel. This will give alpha S beta by 2. Okay. Answer will be option D. So is it clear? Let us solve our last problem of this session. This is the problem that we haven't solved in our previous lab session. So it is related to the method of images. So there is consider a grounded conducting plane which is infinitely extended perpendicular to the y-axis. So there is a plane that is grounded and it's infinity. And if an infinite line of charge per unit length lambda runs parallel to the x-axis at y equal to d. So this is y equal to d, and the charge per unit length is lambda given. Then what is the surface charge density on the conducting plane because of this configuration? So if you look at the method of images, you need to replace this grounded conducting plane by a image line charge density, which is at minus lambda and at a distance minus d. Y, X, and this is Z. If you recall the potential due to a line charge, this we have already calculated it, or you can find out it by using EDL, right? You can easily calculate it by using the Gauss law. From Gauss law, you can take the E. I think E should be around lambda by 2 pi epsilon naught. And when you do the EDL, there will be dr by r. So this will give ln r. So that is why V for plus lambda, it should be lambda minus lambda by 2 pi epsilon naught ln r plus by A. A is some constant, some reference point we are considering. And minus lambda is it's due to V is, if you recall, V is minus of VD. And for the reference point, we are considering this as some value of ln lambda by 2 pi epsilon naught ln. Okay, this is for the plus case. For minus case, only the sign will change. This will be lambda by 2 pi epsilon naught ln, and the distance, let us say this is r minus a. So total potential is V plus lambda plus V minus lambda. We put it, it will B plus lambda is minus of lambda by 2 pi epsilon naught ln r plus pi a. This is lambda by 2 pi epsilon naught ln r minus pi a. So this will give lambda by 2 pi epsilon naught ln r minus by r plus. So that means you can write V x y z is lambda by 2 pi epsilon naught ln r minus. So this is x square plus y plus d square plus z square. And for plus, this is x square y minus d square plus z square. And surface charge density, this you can find out using the boundary condition. So this is sigma minus epsilon naught dou v by dou n. And the surface is at y equal to 0. So that means this is dou v by dou y. So sigma is minus epsilon naught dou v by dou y of This one. This you need to put it here. So we will get minus epsilon naught lambda by, there will be a half because of square root. So we will get 4 pi epsilon naught to y plus d divided by x square plus z square plus y plus d square minus 2y minus d. There will be 3 by 2 here, right? 3 by 2 or only half? Okay, 1 by x. Right. I think, okay, so one thing you can do to avoid this square root, you can add the square root here. So it will give 1 by 4 pi epsilon naught. I think now it's quite easy to calculate. This will give, the first term will give 2y plus t. This will remain same. And this term will give 2y plus y minus t. X squared z squared plus y minus t squared. Put the value of y equal to 0. So this will give minus 4 lambda d by 4 pi square plus z square plus d square. So this is the calculation of surface charge density for a case where we have line charge density. So in most of the problem we have tried to cover the point charge only. For this one is for the line charge density. So is this problem clear to you? This will be our last problem. We'll solve our next problem in our next lab session. Okay. So we'll stop for today. Thank you for joining the session. We will meet on next Friday, same time from 6 to 8 to cover few more problems related to the magnetic induction, electromagnetic induction, the mutual inductance. We'll try to cover that. So please try to join the session, and if you have any doubt, feel free to ask me. So we'll stop for today. Thank you for joining the session. Bye everyone.